So, dear students, let us start with the topic of work, energy, and power. And about work, energy, and power, you might have studied in the early classes on how to talk about the definition of work. And we can just simply say that we can define work as simply as saying the transfer of energy. I think we need to put on a note for understanding sake. You can say work is defined as the transfer of energy. And when you say it is a transfer of energy, we need to understand that there are some certain conditions that must be met before you can say work is done. So if energy is to be transferred, there should be what? There must be conditions. Now, later in the part of this slide, we might be learning about energy as a whole and different type of energies, and as well as conservation of energy. But in this slide, we are limiting ourselves to work, different type of works, and we are focusing mainly on work. And we are going to do illustration as usual. Now, about that, I said, if we say work is just defined as a transfer of energy, excuse me, so we can also write as a, like I said, conditions must be met that work is done. Work is done only when the direction of motion is in line with the applied force. Basically, in early classes, you might have been told that the work done by a body is a product of that force multiplied by distance, which we are still going to talk very well about. But one thing we need to know again is that most of our textbooks and text material define work as a product of force and work and distance. So what we're trying to say now is that no work is done when distance is not correct. So in fact, in junior classes, we were told that if somebody is climbing a stairs, is doing work, somebody is stationary and is not moving, such person is said not to be doing any form of work in physics. So you can say technically that a work done is always the force multiplied by what? The distance in the line of the displacement, rather, in the line of the motion. Why I'm using displacement is because we are talking about what? Direct direction. So I hope you understand this, and to understand that very well, we can quickly consider a block of mass, like my student used to say, I love using block of mass M, that is on a rough plane from what you have studied, is applied to, a force is applied into this block by a boy. Let's say there is a boy. This is a boy. The name of the boy is Lanre. Is applying a force onto this. Don't mind me, I love using that name because it's one of my students I always prepare the slide for us. Now he's applying a force onto this body. So the force is in this direction. From Isaac Newton third law of motion, we have heard about that. And we've studied that early also in the beginning of the mechanics, that action and reaction are equal and opposite. There will be a force that is acting in opposite direction, and there will be a friction. The weight of the block is acting here, which is mg. Everybody knows that. So we now make the force coming to this side to be equals to what? The frictional force we call mu what? N, as N is the normal reaction, which is equals to mg. That we are studying. I'm not talking about that now. So let's say the force displaces what? When forces was applied to this, it displaces this stuff by a distance called delta x. So it has moved from this particular point to this point now. So now we say the work done on this body in the direction of the motion is simply given as a product of the force multiplied by the change in the distance, the displacement, you say what? Delta x, which is also a vector quantity. So next time you have numerical interpretation to that, you should always keep it at the back of your mind that force is equals to what? Force multiplied by what? The displacement in the direction of motion. That is one. Again, we can also look at it that like I said, conditions are to be met. No work is done. We can write that for clarity's sake. No work is done when distance is not equal. When distance is not equal. So this is also an important thing you can keep down. Then again, about the direction of force, you can see this force is acting in the direction of what? Of the block. It is not always, like I said, we have conditions. It is not always when we talk about force sometimes might not be acting in the direction as you might have studied. So in the situation whereby, look at another condition I'm trying to illustrate, the situation whereby the block is not in direction with what? With the force is not in direction, in the same direction. Let's look at the situation. Maybe there is a block of mass, as usual. I love using a block of mass M. A force was acted upon it in this direction. This is the direction of F vector. Force is a vector quantity. And, because of the application of force, there is a grant. There is always going to be a grant. This thing was displaced by a distance of what? Delta x, which we've talked about. The displacement is now delta x because it's going to this direction. So now we can say if this thing was now having an angle of theta to the horizontal, the direction of this, you can see when force was applied in this direction, it has moved this thing in this horizontal direction. The work is only done in this horizontal direction because the direction of the motion is horizontal. When you apply force, the force is not coming in the same direction this time around. It is coming like a slant form. So, but what we need to know that we have only discussed force, a work done on this body. Are you getting it? The work done on this body is now equals to the product of force, right? Which is F vector multiply. Now, if we want to get the direction of force, you can see this is now in components from what we have studied under motion and mechanics. We can resolve this into two components. We now the vertical component, which is sine theta, and the horizontal component, which is cos theta. So we say the horizontal component here, which is the direction of the motion of the block. This is the block of mass M. I hope students are getting this. When we resolve this is F cos theta, and the vertical component, if you want to put it, that is what? F sine theta. So where is the direction of work done of the application of force? Now it is what? F cos theta multiplied by the displacement, which is what? Delta x. So what we are saying here, my dear student, is we can now write this particular formula, F cos theta multiplied by the displacement delta x in vector form. You can watch our video on vector to understand vector as F dot product of x. So this is the way we represent another formula for what? For work done when the direction of angle or the direction in which the force is applied is not in line with the motion. What we use in physics is just for us to use what we call F word. Some people can also put it, you can say it is Fx cos theta. It's another important formula when angle of what is given in the direction of work. So please keep this at the back of your mind. And this is what I call my introduction to work done and what we need to understand. Again, before we move to the next slide, we can also talk about, sorry about this. We can also talk about another important thing. Now, when I explain or introduce you to work done, I say something. There is one thing you need to understand. Work done can also be negative. Excuse me. When we say work is negative, what we are trying to say is that look at this. Look at the illustration we gave. Illustration one we gave here, and that has the second illustration. Now, from illustration one, we can conclude that the direction of force here is in line with the direction of the block of mass M. Now, as we apply the forces in this direction, we can say that, sorry, guys, we can say the motion of this block is moving in line with what has been displaced by x, and we say force times the displacement is the formula we use for work. Now, we say there will be another force, which is frictional force, because this is on ground, which you say mu n or mu r. Some of you call it r in your early classes. It's still the same thing. I'm taking n as a normal reaction acting between the block and the ground. Now, from here, we can see directly that these two forces, are you getting in these two forces now? It is possible for some time for this block to move in this direction. The force applied here must be greater than the frictional force. We studied that also in early classes. Now talking about negative one. Now look at this. Now the boy is doing work on the block. That is why the block is moving from one side to another. Now, in that time, we say in physics, you can keep this in mind, it's very important. Now, work done can be positive, like I said, and it can be negative. Now, when the boy is doing work on the block, that is why he was able to move the block. I said Larry, yes, he was able to move the block to a distance, but what was displaced. Now, if this frictional force now is now greater than what? Than the force applied by the boy to the block. Now we say the block is now doing work. You understand? Because by the time frictional force is also moving it, it has moved it by a displacement too. The block is now doing work on the boy. So this is where we relate. So when the block is doing work on the boy, we say it is negative work done. But when the boy in what is doing what is doing work on the what on this, we say what it is what positive work. So we always have it now. And when we want to explain that or we want to write it down in a note and in your test materials, that is if you have good one, you will see that or sometimes we say work can be what? It can be dissipated and it can be gained. So when you are saying what energy is being what transfer of energy from my definition, before you have energy, there must be some force. And if there is no what, if there is no energy, force cannot be generated to what to do work. Do you understand? Energy, force, and work. These are other things we are still going to talk maybe later part and towards of this topic. So my point now is that when work is what work can be done, when work is done on the body, work is done on the body, you mean positive work. When the body is doing work on what? On somebody now. Work, the boy is doing work on the body. The body is doing work on the boy. You understand that? That is what we call positive. So positive work means, you can say positive work means positive work. I think it's better for me to write that, means loss of energy. I hope students understand that from the way I've explained. And negative work means gain of energy. I hope you understand that. When one is losing work or energy, one will be what? Gaining energy. So because the boy here in context here now, what we are using as for illustration, is doing work on the block. When you are doing work, what are you doing? You are giving out your energy. So when energy is being given out, we say that what? That is loss of energy. But when the block is doing work on the boy, that means what? The boy is what? Gaining energy. So be careful about negative work, positive work, especially in non-numerical calculations. And this is what we are going to talk about here. We'll move to the next. Let's start. Now, in continuation to what we have, guys, we are still on the topic of work, energy, and power, and we are only limiting ourselves in this slide or in this video to the work, the aspect of work. The second video we focus on energy, and the last video we focus on power. And this is the way we want to relate. This is Most Day Academy, and don't forget to subscribe to the channel. So, in continuation to what we have, we are talking about work done by variable forces. Now, students should keep in mind that it is very, very possible for us to have what? To have a body that is being what? That work is being done on from one point, or let me put in a simple language, which everybody will understand. Now, there is a body. Let's say there is a ground. For illustration's sake and understanding, there is always a ground. Yes, there is always a ground. And on top of the ground, there are blocks. As you can see, even though my blocks is not drawn to scale, just manage the block the way the blocks look like. It's shy block. So we have a block, there is a block, and it's placed on the body. So now, because of that, let's say the direction of application of force is in line with that. It will displace it, let's say, to this particular point. And it has been displaced by a distance of what? Delta x, as we have studied. So the same block M1 has been displaced to M2. And what we are having now is that what? The distance is covered from here to here. You can say delta S1, if you write like it. Then to the final product, the final distance, we can say what? Delta S2 by application of force. So when we have a variable force, that is, force is changing at and what? We can change, okay, to understand it very well. I said, what are the concept of our introduction to basis of integration and what differentiation? Because if you want to know physics, you have to know math to some extent. So that is why even on our page, we also provide basis of integration and basis of what differentiation on our physics page, because you need to know that to understand all these things very well. Now, what are we saying here? We are going to take, to understand variable force very well, we take a what? A particular position. Let's say that particular position, the body is still at data x. Now it has moved from, well, let me just say the distance here is s before. So at this particular position, elemental means small, 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 small. So for this small change, you can say it is now moved from here from x to what? To x plus what? Dx. As in, it has started moving from here. You can see that the distance is changing from one point to another. So whenever work done, listen guys, is given as a function of what? As a function of x. Whereby x is now what? Or you can say, let me use the x I'm using for understanding's sake. Whenever work is given as a work done is given as a function of s, what we do is to get the area under the curve of this elemental part we have taken. You can watch my integration, basis of integration. I've done all this stuff. What we do now is what we take the integration of f, then ds. We are taking the limit of distance from s1 to s2. My dear student, this is not difficult to understand, because if you watch, if force is changing, distance is changing at every position. Whenever we have the distance covered from this S1 to S2, as you can see from my illustration, is going to be integration of what? The force, because the distance is moving from S1 to S2. We are comparing what? Elemental change. And students should have it at the back of their mind that force here is the F here is the force, and whereas the S here is what? The change in what? In displacement or distance, as the case may be. So be careful that whenever you can put down a note, whenever work is done by a variable force. Whenever work is done by a variable force, we use integration. We use integration of f of work done formula. So I think it's okay like this. And by numericals, and when we start to understand how we come about that. But what I've given you so far now, my dear student, is for you to understand work done formula is F times S. Work done formula can also be F S cos theta, which you can also write as F dot product of S. Listen, Fs cos theta is written as F dot product of S under what? Our vector relationship. So keep it in mind. And now I said, if it is a variable force, work done is given as integration of F multiplied by what? ds, taking the limit from what? A distance S1 to a distance S2. So that means we need to know the concept of integration to be able to calculate work done by variable force. Then we move to the next slide to explain the next message. The next one is a calculation of work done, which is the last of this, I believe. Calculation of work done using graph. Now, let us keep down a note to understand this concept very well. The area, you can write the area under the force distance or force displacement curve is given as work done. So students need to be careful about this, because some question can ask you to calculate the work done by a body that is under a curve. So we are going to do some illustration to understand that, as we have already studied that when we talk about work done, let's say we have something like this for understanding's sake, and we can have different shape. So this will help, what your knowledge of mathematics is going to help you here, because we are talking about a force measured in Newton and displacement measured in meter. So if you have an area under the curve, it can be anything. Maybe I can take a first one can be maybe something like a triangle. For example, we might take an illustration of triangle. You can see now, if you shade this portion, now the area under this curve now is work done, as in the area of this shape now It's going to give you the value of work done. So work done by the body on this what graph is now the product of what the area is the same, it is F times X, and F times X is the area under the curve. So the area under the curve is what's the shape, my dear student? This is a triangle, and the formula is half base times height. So keep this at the back of your mind. It's very, very important. And that is the first one. Another illustration we can give, which you need to keep at the back of your mind, is a situation whereby we have another curve. So any curve you are having, you need to know how to get the area under the curve. If you don't know how to get the area under the curve or the area of that particular shape, then you have issues in getting work done. So work done is also the same thing as area under the curve. This time I can consider maybe something like a semicircle or a circle or a full circle, anything that is going to give me what I want. So maybe I should consider a semicircle like this diagram, not done to scale. And I am showing you guys that this is also a force displacement graph. Force is measured in Newton, displacement is measured in meter, and you have to calculate the work done of this shape. The work done on this shape is F times S, which is the same thing as area of the shaded portion. Students need to be careful about all these elementary stuff. So area of this C shape is area of a semicircle. Area of a circle is pi r square. Area of semicircle is pi r square by 2. And let it be known that distance from here to here, for example, is what is the diameter. So, and you remember that diameter from mensuration class is equals to 2 times of radius. So you should keep it in mind, because if you are taking the whole length from here to here, you have to what? Divide the answer what? Radius is half of diameter. Anyhow you want to write it. So you have to divide the value from here to here by 2. And it can be a complicated shape, in the sense that when I say complicated, I don't mean what you cannot solve. It is what you can solve. I trust my student. And if it is a complicated shape, like it contains more than one shape, you just need to watch. Let me just use an illustration of your velocity time graph. You might have studied in early classes too. Look at this, my dear student. You have this. The body is moving up to this point. And after reaching that point, it moves a bit with constant. You know this very well. I know you are very good with this. Constant velocity for that point. And after that, the body now retardates or whatever. If it is a shape under what force distance curve, like we have studied, we also use the same thing. We have studied also, you can see force in Newton, displacement in meter. Here we can now see the shape of this one. You have to now bisect. This is a triangle. This is a what? Rectangle, and this is a triangle. So area under the shaded portion, you take it one by one, then you solve. Or you can take the whole shape to be a trapezium. If you know the formula for area under the work done by this body is always force times distance, which is also equals to area under this curve can be equals to area of trapezium is half A plus BH. For many students who have issues with this, where this is A and this is B and the height is this. But if you want to use it one by one, you can also say the work done by the body is area under the curve, as in it's also equals to the area of triangle plus the area of a rectangle plus the area of another triangle. So this is it. And from formula, work done will now be equals to, is the same thing, half base times height. You are adding it to rectangle is length times breadth. You are also adding it to area of triangle, which is half base times height. So this is the way we illustrate or we relate something like this. Students should be careful about this, and it's very, very important for you to have this at the back of your mind. So this is all about this. Then the next part about the work done introduction that we've done is just to solve question on the so-called what's it called? What we call the illustration aspect and the numerical. About the illustration and the numerical, we can quickly consider the next point. Fine. Now about the illustration we have here, we just need to be fast because time is not on our side. Sorry for rushing here. Time is always a major problem when we are doing stuff. Now to understand this critically, we can say the area under a force distance graph represents dash. Now, from what we have studied, we said area under the curve for force distance or force displacement is what? Work done. So we have said this one directly, and I think this is very easy for us to pick. So the second question is, A force varying linearly with a distance acts on the body as shown in the diagram. The work done on the body by the force during the first 10 meter, you can see we are only to consider the first 10 meter of the motion distance. So directly, my dear student, what we need to do here is just to consider only the first 10 meter, and doing that, we can say the first 10 meter will lie at this. And when it lies like that, we can see this diagram not done to scale. I'm just trying to bring out something that will make sense. So the first 10 meters should be this point, and it should touch this. Diagram was not drawn well. So this point here should correspond to this particular point. So what we are trying to say now is that the area under the curve of this particular shape is what we are going to do. So students should be careful sometimes. You have to follow the line of the question so that you don't make mistakes, because most of you will have think this is half base times height. So half base times the height, which is also the same thing, because the curve we are considering here is what is a triangle up to this level. So you can see up to this level. So half base times the height of this triangle is what is 20. And the base, what I'm saying is that I am taking it up to the first. Just the distance is what is changing. So please, I may not actually put this demarcation there. So area under the curve, we know work done formula is the same thing as what? The area under the what? The first distance of area under the curve. And directly, we know the area under this curve is what? Half base times height, which is the triangle. So from half base times height, we can say the work done here is half. Remember, we are only taking the distance, which is the base, up to the 10 meter, the first 10 meter. Then the height here is 20. So doing this one, our answer will be what? 100 joules, which is what? Absolutely good. So that's the question answer. That is the answer. The next one, which is the next slide. I'm sorry about watching you guys. We have a long way to go. About this question, we have a body is under the action of force such that the force displacement graph of the body is semicircular as shown. The work done on the body by the force in moving a distance of 24 meters is that we have studied that work done is force multiplied by the displacement, both are vector quantity, so which is simple as area under the curve. The curve is a semicircle, so the area under this curve is what we have also studied, which is our pi r squared by 2, which is a semicircle. So directly, we know pi. I think answer should be in terms of pi. Pi times, we are considering the what? The value of the radius and not the value of the diameter. So the radius of this thing, see, from here to here is 24 meters. The diameter. Radius is half of diameter. Diameter is 24 meters. Radius will be 12. So I have times 12 times 12. Everything we are dividing by 2. So directly you can say 144 by 2, or you say 12, 2 year 1, 2 years 6. 6 times 12 is 72. So you say 72 pi measured in what? In joules. Work done are measured in joules. And that will be the question answer. So we need to be careful not to make mistake, because we are under what? We are to follow the line of the question. So please, I'm taking, according to the question, I'm taking the formula of semicircle, because this is a semicircle. So we need to be careful. I hope you don't make mistake there. And the next one is okay, diagram not drawn to scale, I can see, but the question here asks us to find, according to the diagram, what is the work done in moving. It's not working, you're not working anything, you are moving. You are moving the block to 5 meters. Well, anyway, we have a block, even though it is not drawn to scale. We can only show you the direction of motion. It is from 2 meters now, we are moving into 5 meters. So you can see, and work done formula is given as a function of what you can see, variable force. So we have force, work done formula in terms of variable force is given by what? Integration of F and change in distance, taking the distance from what point of S1 to the point of S2. So directly here, we need to understand other things, which is also very important. We need to integrate the force. Remember, initially, we know work done is force times distance. And it is outlined, the force is going in this direction, not shown. So, and we know at this direction, the force is what? F cos what? F cos theta. We discussed that. So F times cos theta. So cos of the angle here, I have to put into consideration. So if I'm writing my formula, it should have been integration of F cos theta. And the cos theta is what I'll do first. Here I have cos of 60 degree. This is 60 degree. Cos of 60 degrees is 1 over 2. So the integration of, I'm taking it from the distance of 2 meters to a distance of 5 meters. So we are taking this from 2 to 5. I'm integrating the function of the force, which was given as 3x squared minus 2x plus 1. Now, our knowledge of integration is needed here because we have to do 1 by 2 is outside. Where is 1 by 2 coming from? Cos of 60. Then the formula is the integration of f ds. So I'm now doing it that integration of taking limit from 2 to 5. When you integrate 3x squared, for those who are yet to watch our video, go and watch. I want to tell you integration of ax squared is ax n plus 1 over n plus 1. That is, add 1 to the power, divide it by the what you have as the answer to the power. Here, what is the power? 2. 2 plus 1 is 3. Divide by 3. 2. 3 by 3 we cancel out. This will give you x cubed. This one also is in power of this one is 1. 1 plus 1 is 2. 2 we cancel 2 over 2. That is x squared. And whenever you integrate what this will give you something like x, because this one is having x to the power 0 plus 1 over that. So this one will give you what? Plus x. When you integrate a constant, it's going to be a variable. So now we are taking the limit from 5 to 2. The interpretation of this one, my dear student, is when x is equals to 2, when s is equals to 5, minus when s is equals to 2. So we are going to do that. So we have x cubed minus x squared plus x, taking the limit from what? 2 to 5, that is 5 and 2. I will substitute and we do it together. When s is 5, let's do it together. 5 raised to power 3 is 125 minus 5 raised to power 2 is 25 plus 5. Be careful. This is 120 plus 5 again. This is 100 plus 5. It's going to give you 105. When s is equals to 2, you do that as well. 2 raised to power 3 is 8 minus 2 raised to power 2 is 4, then plus 2. Answer to that one is giving you 8 minus 4 is 4, 4 plus 2 is 6. So what do you have here, my dear student? You are having the answer of 1 over 2 times, we said we are subtracting the upper limit from lower limit. Subtracting this value, my dear student, you are going to have 99. I think I am right. Yes, absolutely. So this will be half times 99. So our answer will be something like 99 divided by 2 will be 49.5, if I'm not mistaken. 49.5 joules will be the question answer. So this is the way we solve questions on variable force. You have to integrate and you take the limit from one point to another. So students will keep variable force at the back of their mind, and as well area under the curve is also very important. So guys, sorry for rushing this video. I have fishes to fry. See you guys soon in the next one, whereby we'll talk about energy, and the last part of this we'll talk about power. So bye for now. Thank you.